have talked about LFSR based pseudorandom pattern generator using say means weight of 0.5 and any arbitrary weight power of 2 in our last lecture. Now, in this lecture we will be talking about the next thing we need to do in built-in self-test, namely how to compress the response compaction. So, before actually telling you how we do it using an LFSR, let us first introduce some terminology and some basic concepts, but first let us see what this response compaction actually involves. Okay. Now, you recall that in a built-in self-test environment, we are feeding the cut circuit under test using a large number of LFSR patterns, typically in the order of thousands. So, the cut output response generates huge volumes of data. Just an example, suppose using LFSR we are generating 4 million random patterns, which is very typical, and this circuit has 200 outputs. So, the amount of output data which gets generated is about 0.8 billion bits. Now, this is clearly uneconomical to store this 0.8 billion bits and compare them individually with the corresponding fault free response. Of course, this would have been the best thing if we could have done that, but since it involves such a huge volume of data, we cannot afford to do this. So, it is mandatory for compacting the response in some way before comparison. Of course, compaction should be such that our confidence in the quality of testing should also remain high. It should not be that we are making a gross compromise on something. By compaction, we are trying to remove the problem of storage, but the quality of testing is going down. That should not be the case also. So, let us see what is done in practice, but before that we try to give some definitions. See, we are doing some sort of a compaction from a, you can say, bigger or larger response, we are trying to compact it into a smaller one. So, whatever algorithm we choose, there is always a chance that two different responses may get compacted into the same so called signature. This is something which is called aliasing. Signatures of good and some bad machines may match. Because we are doing compaction, compaction means we are leading to some information loss. Like a 1000-bit data, you are compacting into a 16-bit data, for example. Naturally, we are incurring information loss. Say a 1000-bit data had 2 to the power 1000 possible combinations. Now, a 16-bit signature has only 2 to the power 16. So, naturally, two patterns can always match to the same signature, they can map. So, there will be information loss and hence aliasing. The process of compaction involves a drastic reduction in the number of bits. Since we are reducing the number of bits, naturally this involves information loss. Compaction is used in built-in self-test. But we have another related term, compression, but compression is used in a different context. Compression also tries to reduce the number of bits in the response, but using some well defined algorithm so that the original response could be restored by using a reverse algorithm. So, there is no information loss. Like in a computer, when you use a compression program like compress or WinZip or something, so we know that we can again come back to the original one by using a decompression algorithm. So, compression decompression is something different. We are trying to compress or reduce as far as possible, but we are keeping sufficient amount of information so that we can also perform the reverse mapping in some later stage. So, we do not lose any information later. So, actually it is not compression that we are interested in, we are interested in compaction. Now, the method which is used in BIST is traditionally called signature analysis. It says that you compact the good machine response into a small value which is called the signature. Now during testing, you again compute the signature and compare the signature with the good machine signature which you stored in a ROM. Say in a ROM you stored the good machine signature, and using a response compaction block you generate the signature during the actual testing. These two values you can compare and you can report if it is good or bad. This is the basic idea. Now LFSR in the signature analysis and response compaction, this has been traditionally used much before this testing came into being. In fact, if we look at this linear feedback shift register for response compaction, well, this compaction uses the same technique which has been used since long time. Well, you must be familiar with the cyclic redundancy check code which is used in a wide variety of application like your disk subsystems, input output, networking. So wherever you need to check for some errors, bit errors, you use a CRC checksum at the end of the message so that you can recompute CRC after receiving and compare if they match. Okay. So LFSR for response compaction, what they do, that is exactly similar to the CRC check code generation. Now the way CRC operates, I am not going into detail. See, you have an LFSR. Now this LFSR realizes a characteristic polynomial. Okay. Now you feed the LFSR with a stream of bits, a 0-1 pattern. Okay. Now this input bit stream, you can treat that the bits are forming the coefficient of a polynomial Qx. If Px is the characteristic polynomial of the LFSR, then what you do is that you are actually dividing the polynomial Qx by Px and generating the remainder polynomial Rx. Rx is the remainder, okay, after division. So whatever is the remainder polynomial, that is treated as the CRC code or the signature in the present context. So after all the patterns have been applied, the way the LFSR response compactor is designed, automatically whatever data remains here at the end, this is the remainder Rx. But in order to do this, initially the LFSR must be initialized to all 0. But here there is no harm in putting all 0 because, well, some data is also coming from outside. So there is no fear that the LFSR will get stuck into the all 0 pattern like it was for the pattern generation case. Okay. So what you do, that after the testing is complete, you complete signature whatever is there in LFSR to the known good machine signature. Of course, you must compute the good machine signature through simulation beforehand and store in a ROM. Okay. This is the scheme. So now let us see how using LFSR you can compute the CRC check word or the signature. It is fairly simple. Well, of course, LFSR can be designed in a number of different ways. This is an LFSR with internal XORs. Okay. So here I am showing an LFSR which realizes the characteristic polynomial x to the power 5, x cube, x and 1. These are the coefficients. Now you look that from which points we have taken the outputs. This corresponds to x to the power 5. Here x to the power 4. This one x to the power 3. This one x to the power 2 and this one x. And of course the input, this is treated as 1. You see we have XOR, of course the output will always be fed back, so x to the power 5 will always be there. In addition, you have connections from x cube, x and 1. So, these are the terms which are there. So, given any characteristic polynomial, you can construct the corresponding LFSR like this. Now, the only difference from a pattern generator is that in a pattern generator you did not have this XOR, rather this line was directly connected to the input. But now you have an additional XOR in the input stage where the input bit stream is being fed. Of course, a clock is there and the LFSR is initially loaded with the all 0 pattern. So, now the circuit responses are coming, you are applying the clock and whatever response remains finally here, that is the remainder polynomial and that is the signature. So, the concept of signature compression or response compaction using LFSR is very simple in concept. You can use a very simple structure like this LFSR to do both pattern generator and response compaction. Now, since the structure of the pattern generator and response compaction are so similar, now you can understand why you can easily build a structure like that BILBO, built-in logic block observer. That was a general purpose structure which depending on your requirement you can configure it as a test pattern generator or as a response compactor. Okay. But first, now let us try to analyze some issues related to the aliasing probability, that we are compressing a very big stream into an LFSR signature where number of bits is equal to the number of flip flops in the LFSR, typically 16 or 32. So, what is the price we are paying, or what is the chance that a fault may occur, but we are unable to detect it? The faulty signature is the same as the good signature. So, let us try to make a simplified analysis of the so called aliasing probability. Okay. So, aliasing probability, as I had said, it is the probability that an error has taken place, but we are unable to detect that error. So, aliasing actually means that there exists some error in the bit stream, but even in the presence of this error, the final signature does not change, which means that we are unable to detect this fault. Now, let us try to do a simplified analysis of this problem. Let us say that we have a n bit data stream and we have a m bit LFSR. Typically, or for most practical purposes, the value of n is much larger as compared to m, because n can be of the order of millions and m can be of the order of 16, 32 or 64 maximum. Okay. Now, here let us try to see what does this mean. We are trying to compress an n bit pattern into an m bit LFSR. So, we have a response compactor block where at the input we are feeding an n bit data, as the output we are getting a m bit compressed response. So, what does this mean? This actually mean is that, well, the input was n bit. Okay. Now, in n bit we can potentially have 2 to the power n possible combinations, and similarly for the LFSR, for m bit we can have 2 to the power m possible bit combinations. So, it is always the there is a chance that several of these 2 to the power n patterns might get mapped into the same m bit pattern out here. This is what we term as aliasing. See, if this is the fault free signature, for example, then if two patterns map into the fault free signature, then means some of these patterns will also be the faulty pattern, one of them will be the good one, the other will be faulty. So, even if this kind of fault takes place, we will not be able to detect it. Okay. So, let us see that what is the chance or probability of this thing happening. So, what we have just said is that we have 2 to the power n possible data streams, and we have 2 to the power m different signatures. Okay. Now, from these we are trying to find out number of data streams that map into the same signature. This will be 2 to the power n by 2 to the power m, assuming, well, here we have made a gross assumption, we are assuming that the patterns are uniformly distributed with respect to where they map. Okay. It is not that more number of patterns are mapping to this signature and few number of patterns are mapping to some other signature. No, we are assuming that there is a uniform distribution. So, number of data streams which can map into the same, that means I am talking about the cardinality of this, which can map into the same signature will be approximately equal to 2 to the power n minus m. Okay. So, this is a factor, and from this we can try to, we can find out the probability of aliasing. Now, we can find out the probability of aliasing as follows: P equal to number of input patterns which map into the same signature, just what we have just calculated, number of input data streams that map into the same signature 2 to the power n minus m, divide by total number of patterns. This is the probability of aliasing. Okay. Now, this, if you see, it becomes equal to 1 by 2 to the power m. So, you observe one interesting thing that well, of course, we had made some assumption like uniform distribution of the patterns, but the result we have got is that we have got a probability which is independent of the number of bits in the input stream. This depends only on the size of the LFSR. For example, if m equal to 32, then your probability becomes 2 to the power minus 32. 2 to the power minus 32 means what? This is less than 10 to the power minus 9. So, you can see that using a 32 bit LFSR we can get an aliasing probability which is sufficiently small, and because it is sufficiently small we can get a fair good amount of confidence in the, you can say, in the chance that we are detecting an error when it occurs with respect to this scheme. Because of this small probability that we get out here of aliasing, people use this with fair amount of confidence. Okay? Fine. Now, there is an issue. Suppose we have talked about how we can compact a bit stream using an LFSR, but suppose you have a scenario like this. you have a circuit and a test. These are the inputs, but instead of one output, say there are 4 outputs. So here what do you do? If you have one output, you can use a straight away an LFSR out there and do it. So here you can have 2 alternatives. Alternative 1. So alternative 1 is something like this. You have your cut, the circuit and a test. You have the 4 outputs, and to all the 4 outputs you connect a signature compactor. These are all LFSRs. So if there are k number of outputs, you will be using k number of LFSRs for response compaction. Now here the drawback is that you are requiring to use so many LFSRs, but the advantage is that you can compress all of the outputs in one go. So you will have to apply the patterns only once. The other alternative is that you can somehow save on the LFSR. This alternative 2 is something like this. This says that you again have your circuit and a test here. You feed them with inputs, and the 4 outputs you first feed them to a multiplexer. And the output of the multiplexer you feed to an LFSR. This is the LFSR. Of course, the mux will be controlled by the test controller. Now, here you can see that by selecting the mux inputs one at a time, you can compress one of the circuit outputs at a time in the LFSR. So the advantage is that you are saving on the LFSR, one LFSR will do, but the price you are paying is that the testing time is going up. Well, for testing the circuits, you will have to apply these patterns, all these patterns 4 times. First time for output number 1, again you repeat it for output number 2, again for output number 3 and output number 4. So the first alternative requires more hardware but less time. This alternative requires less hardware but more time. So we have to do something where we can get an acceptable solution with you can say less amount of hardware and also less amount of testing time. So some people proposed an extension to the linear feedback shift register. This is called multiple input signature register or MISR. So this is what we have just mentioned with the diagram, that if you use ordinary LFSR compactor one with each output, then we need too much hardware. So solution is to use a signature register where there are multiple number of inputs. You can compact all the outputs simultaneously into one LFSR. This is the crux. Now this MISR, the way it works is that because LFSR has a linear property, well, I am not going into details of this, it obeys superposition principle. So what will happen is that suppose you have a circuit with 4 outputs. So if you compress these 4 outputs individually, you will get 4 different signatures S1, S2, S3, S4. Now if you compress all of them together using an MISR, the signature you will be getting is actually the XOR sum of this S1, S2, S3 and S4. So final remainder will be the XOR sum of the individual signatures corresponding to each of the outputs. So this is also quite acceptable in terms of testing. So MISR is also a structure which is quite popularly used, and MISR looks like this. This realizes the polynomial x cube x plus 1. This is x cube, x square, x and 1. You look at the feedback path has a connection here, it has a connection here and of course in the input. So it is x cube, x and 1. but in addition we have now one XOR gate with each stage and an additional XOR gate. These XOR gates are used to feed the input data. Of course, this is another input, this is one input and this is one input. So, externally you can feed 3 inputs together, this D0, D1 and D2. So, as if now you have a structure, a signature register which can accept 3 bit streams together. Now, if you have a 32-bit register, you can compress 32-bit data stream at the same time or simultaneously. So, this is how an MISR works. Now, using MISR, a number of, you can say, built-in self-test schemes or architectures have been proposed, which can be used for self-testing and also for DFT in some cases. Well, one such popular structure I am showing now. This is a structure called STUMPS. STUMPS stands for self-testing using multiple input signature register and parallel, well, SRSG is serial random sequence generator, STUMPS. So, here the architecture looks like this. Suppose you have a circuit out here, this is a circuit and a test, this is a sequential circuit. So, the sequential circuit can have many flip flops. Now, the flip flops you have configured them in possibly more than one scan chains. You can use a pseudo random pattern generator where each of the individual bits you can use to feed the individual scan chains, and the outputs which you get you can compress using an MISR. This architecture says that a DFT scheme using a scan path is not necessarily used always in conjunction or connection with a deterministic test pattern. That means, you did not always have to apply the test patterns deterministically from outside, and you need not have to just observe the responses by shifting them out always, but rather you can use a scheme like this also, where you have these scan chains in place, you apply some primary inputs, you can apply again some pseudo random patterns if you want, and to the scan chains also you apply pseudo random patterns. So, you can apply pseudo random patterns here, you can apply pseudo random patterns here. In the primary outputs also you can do a compression. So, you compress values and the final compressed values only you compare. This method also has been found to work pretty well, because before just adapting any such method in actual practice, you will have to find out or evaluate through simulation that how good or how bad this method is, and well, means what are the implications of using it. You will have to evaluate the fault coverage through simulation a priori, of course, before actually implementing a BIST scheme. Okay. So, to summarize these BIST schemes which we have mentioned, this linear feedback shift register pattern generator and multiple input signature register response compactor, structures based on these are preferred in BIST architectures. The preferred BIST methods use these, but you should also keep in mind that BIST has its own prices, that you have some overheads that you should incur. Well, the more complex your architecture is, the more complex will be your test controller, because it is the responsibility of the test controller to control the different BIST subsystems, response compactor, pattern generator, who will be activated when, and when we will be comparing the response. So, everything has to be controlled by that controller, which is actually an FSM, it is actually a finite state machine. And since you are introducing some extra gates and multiplexers in the critical paths, your circuit delays will increase. Of course, input muxes are there. You need pattern generators and response compactors. not always you will find some, you can say, some register which was there already in your circuit, which you can expand or extend as a billboard register to act as them. Sometimes you may need to add an extra, you can say, response generator or a pattern generator. So, and in addition you need some DFT schemes for the purpose of initializing the circuit, because BIST is fine, but you will also have to initialize the circuit to a known state, particularly if it is a sequential circuit. If it is a sequential circuit and if you cannot reset the flip flops to a known state, your signature can also vary. Okay? So, you will also have to have some kind of scan path kind of a thing, so that you can set the circuit into some known state, and from there you can apply the stimulus and you can find out the signatures out there. Okay. But overheads are there, of course, but BIST also offers a number of advantages which are pretty attractive. Now, the most important advantage you gain is that you can test the circuits at the full operational speed. If the circuit is designed to work at a frequency of 2 gigahertz, your test pattern generator and compressor can also work at 2 gigahertz. Okay? This is called at speed testing, which I had mentioned before, and this at speed testing you can use for detecting staccato faults. It's okay. Now, in addition, you can also test some additional kinds of faults called delay faults. Delay faults occur or show because of some, you can say, mismatch of tolerances in the delays of the circuit components. Due to these delay faults, there can be some signal glitches and hazards that may occur in the circuit. Now if you are doing at speed testing, there is higher chance of these delay faults to show up as compared to testing at a slower frequency. Okay? And since you essentially do not need an expensive ATE to do this, drastic reduction in the cost of automated test equipment, and you can test it in your own lab, in your field of work. So, you can have it a field test capability. So, you can build a system, the system will have a self test capability. It is not that the chip has to be tested by the manufacturer only at their own site, and they will be delivering the chips to you finally. And since you have these interesting features, you can have faster diagnosis during system test. Of course, less effort to design testing process is very important, because you are eliminating essentially the process of test generation, because you are not using any conventional test generation algorithm. Of course, here there are both plus and minus points. Since you are using pseudorandom patterns as your input stimulus, it is likely that you may not get for all circuits a sufficiently high fault coverage. Okay? But the advantage you gain is that you are eliminating the expensive process of deterministic test pattern generation. Okay? But these are the trade-offs you will have to look at and accept. And of course, shorter test application time, because everything is done inside the chip and at a very high frequency, the total test application time also gets reduced. Okay. So, we have looked at some schemes for, of course, earlier we talked about methods like test generation and fault simulation. Subsequently, we talked about design for testability techniques, which are very essential to crack hard circuits like sequential circuits where there are a lot of flip flops inside. And then we talked about built-in self-test techniques, where you can use in addition some more hardware, where the stimulus generation and response compression can also be done on chip. But manufacturers and industry people, they faced some problem earlier, because these schemes were well understood and well accepted, but there was some lack of standard. Like if there are two companies, say X1 and X2, So, x1 brings up a chip, x2 also brings up another chip with all these testability features inserted. But if I want to design a system employing these two chips from two different companies, so how do I make, or how do I design a scheme for system test? So, is there any feature so that x1 and x2 can work hand in hand towards the testing? So, industry people realized that since there was a lack of standard in this of testability features, well, schemes were proposed and schemes were accepted fine, but there were no standards as such. So, they felt that there has to be some kind of a standardization, and well, the first effort, or the first step in the standardization process, this was taken up by a joint committee, and they came up with a scheme called boundary scan. Now, the committee which came up with this standard, they included almost all the leading industry people, and the consortium was called Joint Test Action Group, and this JTAG name has become so popular that this boundary scan is sometimes also called synonymously as the JTAG standard. Okay, JTAG and boundary scan are today used together synonymously, because you can today look at some chip, say for example some FPGAs, some FPGA chips you buy from the market, you will see there in the pin nomenclature some of the pins they have called these are for JTAG compliance. JTAG compliance means they have a boundary scan feature inbuilt or embedded in the chip. Okay, they call it JTAG. Now, using this testability standard, what we achieve is that this standard allows test instructions and test data to be serially fed into a circuit under test. See, test instructions are something which is new, which means you are encountering here, because you see all the chips may not be of the same type. Some chip may be using conventional scan path based DFT, some chip may be using BIST. So, externally when you are instructing the chip to do something, it is something similar to giving a small test instruction, that means what kind of test you want to do. Okay. So, this JTAG standard, this includes a set of such test instructions in the standard architecture itself, and using this test instructions you can feed the test data, and you can also read out the test results. There are also some special run based command, so that if you have a built in self test feature embedded inside a chip, you can activate that. Normally we will be having DFT scan path thing, so that you can activate scan path, you can feed in data, you can scan out the response. But if you have a complete BIST thing inside a chip, you can also activate it from the outside. JTAG is totally hierarchical in nature. It can operate at the chip level, at the board level, printed circuit board level, and even at the system level. JTAG allows the separate testing of components and also the system interconnects. Now, the essential idea behind JTAG is that, say you have a circuit under test or a chip, okay, I am calling it COT in general, this is a chip. Now, you want to embed a boundary scan standard on top of this. So, what you do is that you have some kind of a so called test wrapper which you build around this. Now, test wrapper is a fairly complex piece of hardware, we will see shortly. There are a number of features in this test wrapper. Now, through this test wrapper you can activate the different testing mechanism in the cut. You can, well, in case of normal operation you can say that well I want to just apply the inputs to the cut in the normal operation mode. Now, in the testing mode there will be features to activate scan paths, to activate BIST and so on. But I am showing you a very rough high level diagram of this wrapper, what are the essential things which are inside, and you can appreciate that this will be fairly complex. You see, this is the total chip, and inside this was the circuit under test which I was calling, this is the system circuitry, and these are the, or these were the input output pins. Okay. So, the input output pins which were there, now what you do, you put a flip flop just along with each input output pin. This is the boundary of the chip. Okay. Well, whatever you do inside the circuitry is separate, but in addition in the boundary of the chip you provide a scan path. This is why this method is called boundary scan. There are flip flops just with each IO pin, they are chained into a shift register. Okay. These IO pins also feed the system circuitry, as you can see. So, using these, when the need arises you can use them to activate BIST inside or DFT inside. If there are scan paths inside the circuitry, you can scan them in, scan them out. Now, inside, in addition to this, there are a lot of other things. For example, out here you have an instruction register. Now, in the instruction register is actually a register comprising of a few number of flip flops. Now, you can shift in some bit pattern here, and now depending on the bit pattern, the kind of instruction you are trying to execute, that will be interpreted and executed. This instruction register can be fed through this test data input. There is something called a bypass register. Bypass register is sometimes used if you are using several such chips in cascade. I will just show a diagram shortly. Several such chips in cascade, and through the test data input you want to program all of these chips one after the other. So, the first one you can do using this path, the second one you can follow a bypass path through this. This is a bypass path. So, you can use the bypass path to access the next such chip which is there in sequence, and in the bypass part in addition there are some device ID register where the device ID of all these individual chips can be stored there, and means when you are sending the TDI you can also specify the device ID, it can check automatically and do it, and all these things are controlled by a test access point controller, tap controller, and there are some signals like test mode select, reset, clock and so on. So, as you can see that embedding boundary scan in a chip is a non-trivial task. Here you need to add a lot of additional circuitry in addition to your circuit, and as compared to schemes like boundary scan or scan path you need to add a lot more. Now, the advantage you gain is the flexibility of the chip you get finally. You will see that if you have boundary scan implemented, you have a number of advantages using which you can diagnose and test chips, boards and systems using the same kind of scheme or technique. Now, as I said that you can have several such chips connected in cascade. Say this diagram shows 3 such chips connected in cascade, and I am showing not all, some of the registers only, instruction register and data register. So, when you are feeding the instructions, it will be following this path. So, actually for this you have the bypass registers, but in this diagram I am not showing the bypass register, I am showing as if they are following these paths and they are rippling through, and you can load the instruction registers of all these chips through these paths. Now, in addition, you have the actual data registers. Data registers are actually the boundary scan cells. These are, through the same TDI input you can access these data registers. Okay, these data registers you can access. These boundary scan cells, they actually comprise the data register. So, when you are actually testing scan in and scan out, you will have to use the data registers. So, this diagram illustrates instruction register loading. So, you can load the instruction registers, and means there will be some multiplexers in the output. You will have to select this to the next stage and so on. Now, the advantage of boundary scan primarily is not for testing individual chips, but for testing a number of chips when they are lying together in a board or in a system. Okay. So, first let us see that when there are several such chips with boundary scan or JTAG capability embedded in it in a board, what are the advantages we gain. Okay. This is an example I have given. This can be a printed circuit board which consists of 4 chips. These are the 4 chips I am identifying. This is one, this is one, this is the third one, and this is the fourth one. So, it can be a printed circuit board with 4 chips, or it can be a multi-chip modular. So, multi-chip module is actually, there are 4 different chips which are put inside the same IC package. So, although it looks like a single IC, but inside the IC there are 4 chips put inside. So, it can work similarly for both. So, what it says that if each of these 4 have boundary scan capability, then the boundary scan register can be chained together. Like the test data in which is entering the printed circuit board, this can go into the boundary scan register of this chip, it can come out of here, it can feed the TDI of the next chip, it can again come out of here, it can feed the TDI of the third chip, it comes out of here, and it can feed the TDI of the fourth chip and can finally come out of here. Now, the advantage we gain out of this is that, well, at the level of the PCB we have a single TDI and a single TDO. Well, if we had sufficient number of pins, we could have had 4 TDIs and 4 TDOs, so that we could have tested them together. But the main advantage of boundary scan is that if we have this, you can chain them all together and you can shift the test data serially, so that we can access all the boundary cells of all the chips inside, and we can do scan in and scan out of all of them together. Now, this is the advantage which boundary scan offers. Now, these chips can now be coming from different manufacturers also. It is not necessarily that they are manufactured by the same company. So, if they comply with the JTAG standard, they can put these chips on the same board and yet have the capability of boundary scan. Now, it is not necessarily true that always you have to chain all the chips together in the same scan chain. So, I have another example. Here also there are 4 such chips, but we have some kind of parallel operation. So, it is up to the user, it is up to the designer, that means what kind of testing mechanism is desired. So, you can have parallelism. Okay. Here you see TDI, the test data input, is feeding 2 chips simultaneously. Similarly, there is another test data. Okay, this TDI is feeding these two together, and you look at this one. So, after falling through this chain, this is entering the second chip. Similarly, this one is flowing through like this. TDO is 1, they are all tied together. So, it says that you can parallelly test these two, but since you have one TDO, you can do it one at a time. But if you have two different TDOs, then you could have tested them together parallelly. Okay. So, it depends what kind of resource you have. You can have some chained together, you can have two blocks which you can do in parallel, and so on. So, this boundary scan is a very flexible method using which you can carry out, or you can plan your testing activity, exactly how do you want to do the testing. Now, just to give you an idea regarding the kind of signals that we have in the tap controller, test access port controller. So, the tap controller, this was shown in the diagram previously. So, just I am showing the diagram once more. This diagram has so many signals. Okay. These are all going into the tap controller. So, I am showing, or means I am briefly telling you about the signals here. Of course, you have a clock, test clock input. Now, during testing you can run this clock at a different rate from system clock. It is not necessary that it should run at the same clock frequency. There is a test mode select pin. So, here you can switch from normal mode to test mode. There is a test data input through which you can scan in the test data, you can also scan in instructions, and you can do it in parallel. You can use it to shift in vectors of one or many test instructions. So, you can basically shift in data which can go to one or more than one such boundary cell modules together. There is a test data output which can serially shift out the results. There is a test reset. Well, this is optional, where just using which you can reset the tap controller, because tap controller may be in some state, you want to reset it and you can start a new testing cycle. So, this test reset is a signal using which you can reset the tap controller FSM. And I am not going to detail, these are some of the typical instructions which are there in the boundary scan: sample, preload, execution test, in test, run test. There are many. So, using this you can test the functional modules, you can test the interactions, you can just run BIST inside a chip, and there are a number of other schemes also. You can put one of the modules into the bypass mode and so on. So, it is quite flexible in that sense. Just to summarize, boundary scan has emerged as a standard, and there are many chips and products which are now in the market which are based on this standard. If you have multi-chip modules, for example, in a chip, so unless you have boundary scan standard, it is very difficult to test such. And boundary scan standard is totally flexible, it supports built-in self-test, it supports external testing with ATE, and you can have scan chain reconfiguration also. And it has been widely used in many environments in the industry. So, here we try to give you a very rough overview about the essential idea or the concepts in the different aspects of testing process. We talked about test generation, fault simulation, design for testability, built-in self-test, and boundary scan. But we only try to give you you can say an introduction to the problem, but there are a number of other problems involved, related problems involved, which need to be tackled, need to be addressed, need to be solved if we want to have, or means if you want to arrive at a chip or a design or a testability scheme which is practical and cost effective, and of course it will be attractive to a large community of users.